Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 30, and we are going to discuss regression, the first part, which is straight line regression. And this is in chapter 10 of our textbook. So we're going to, of course, start with our header information, which we don't want to change. We'll run the chunk for the settings, and then we'll resize our console back down here and then run through our packages, and you can see information's being given down here about what's happening with the packages. And so it is important to know what's being printed out here because this tells you if you have to change your code in order to call something. See, we're attaching psych, and then it's saying the following is masked. In other words, if you call logic, this logic function, you will not get the base logic function. You're going to get the function from the car package, or not from the car package. You're going to get the one from the psych package. So if you want the one from the car package, you're going to have to specify that it's from the car package by saying colon colon car colon colon logic, and then using the function. Okay, so it is important to know sometimes what is being masked. So if you try to use the mean, you're not going to use it from the matrix package unless if you want that one, then you have to call it specifically again. Okay, and then we see now the psych package has been masked, so logic is not going to be available from psych. It's going to be available from some other package. Okay, and so forth. So this can complicate how we do things, but it's important information to know. We just don't want it to print out in our PDF. But if you need this information, it's all there for you. All right. Now, we're going to look at an example that's quite common, that has been looked at a lot in classes, and it's called the age of chicks. And we're trying to predict their weight based on their age. Okay, so we're trying to predict the weight based on their age, and then in the data we have the log of their weight as well. So this is not lined up as well as I had hoped, but that's okay. It's just formatting. And well, we can do that. So we have the days in the first column, the weight in ounces, and then the log of that weight. So anything that's less than 1, when we take the log of it, it becomes a negative. Okay. So we've got our column names here, and we don't have a column for order, so we have commented out these two lines that order it based on that variable that we don't have. So if you did have the order, you could uncomment these, and then you could use those. All right. And then we're going to print out, I believe, did I run this? I thought I cleared all output, so it must not have stuck. All right. So we're going to run this, and we've got our table here. And then we're going to look at descriptive statistics. So here we have weight, age, and log weight. You'll notice that unlike in the ANOVA, I have to do these as separate entities. So this would require you, if we have more than 3 variables or less than 3, you're going to have to redo these. Okay? So, and then you see I have variables where I've added them, put them all together. So again, if you have more than 2 or more than 3 variables, you have to add that here, and then you have to add the name to this concatenation here so that it is included in the output. All right, and you'll have to add it here as well. So this takes a little bit more than the descriptive statistics from the ANOVA, and that's because there's just no good way for FabStats to handle these different variables that are in different columns. Okay. Now we could make it all in one column, but we don't need that. We don't want it that way for our analysis. We want them in different columns for the regression, all right, as we'll see. So we take a look at this and we look at the medians first, and we see that the weight median is the smallest. Log weight is, or actually log weight is negative, and then age is around 11, and that's just the middle value there. So age is not very informative, since we have one for each day that they were, so for one for each day, all right, one value for each day. Now, then we have the means, again, negative up to 11, and the standard deviations go from 0.65, 0.9, and this is just because we have how many days? We have 11 days, so we have from starting at 6 days up to what, 17? 16. Okay. And then we have a scatter plot that we can run. And it's important that you run a scatter plot before you do regression. And this is why. Because we do not have a straight line here. We have a curve. This looks like a parabola that's been rotated. Okay? So we cannot do straight line regression on this. We can, and it it approximates a straight line in a way, but it's not the right shape, so we should not do it. And if you ran the regression on this, it will tell you that the intercept and the slope are significant for a straight line, the line that's drawn here. But that is not the line I would want to use to predict the dry weight based on age, because it's going to, up here it's going to be very far off, and down here it's going to be very far off, and in the middle it's only close for these 2 days and for these 2 days, maybe these 3 days. We're looking vertically, so it's only close for 3 or 4 days out of the whole range of our data. So this is the wrong model to use. So what are we going to do? We're going to use the log of it, and the data was supplied to the log base 10 of chick weights. And so we're going to look at that, and these here give us the regression, and we'll talk about that more, but we're doing this just to plot the line so we can see how it fits the line. And now it's almost a perfect fit. This is a very good fit. Now, a very good fit will cause us some issues, it turns out, when we come to analyzing the assumptions for this. Because it's such a good fit, it's going to make our ranges really, really small. Okay? But I don't think anybody would look at this and say that it's not a straight line. All right, so we're going to use the log base 10 to do the analysis. And so this is going to be our model. So it's the log of the weight, and here it's the log base 10. The log of the weight, and maybe I should put that, because in statistics, when we say log, we normally mean the natural log, but here they did the log base 10. Okay, and the natural log works too, but then you'd have to create that yourself, which is easy, but again, not something I'm expecting you to do. All right, not in this course. Okay, so here's our linear model, and so we take LM for linear model, and we take our Y variable, which is going to be weight, and then our X variable is age, and specify which data. And then we do the summary of that to get the regression output. So we have the 5-number summary for the residuals right here, and we see that they're very small. The residuals go from 0.049 up to 0.034. So this is a very small range for the residuals. And this may cause us some issues when we're looking at the equal variances, we'll see. All right. Now, the coefficients here, this is where we test whether or not they are significant. The first is the intercept. It gives us the estimate for the intercept and for the slope. The slope is age, for age. And then it gives us the standard error, which we could use to calculate confidence intervals, and the t-value that's calculated. This is our test statistic, and then the p-values for each of these. And we see that they're both highly significant. Okay, this is a very good fit. When we come down, we would want to, one of the ways we measure how good the fit is through something called the adjusted R-squared. We're not going to get into that, but the higher the number, the better. And look at our numbers, 0.9981. That means that the R value, the correlation coefficient, is the square root of this, which makes it even closer to 1. In fact, when I take 0.9981 and I take the square root of that, I get 0.9990. Okay, so our correlation coefficient is extremely close to 1. And we should be able to tell that from our scatter plot, where the points almost, well, I think all the points actually touch the line, although they're not all on the line. If they were all centered on the line, it'd be a 1. But this is about as close as you can get. So this is an excellent fit. And then the p-value for the overall fit of the model is given down here, the F statistic. And that is a very high value of an F statistic, 5.356. That's huge with 1 and 9 degrees of freedom, p-value. Okay, so if we want to look at the overall fit, it's given on this last line. So that's an important thing. I didn't address that here. I addressed the intercept and the slope. So the slope for a single level regression is what tells us mostly when this is a significant model. Okay? All right. So its p-value 8399. Okay, so yes, it's just a rounding thing. You'll see that this is one more decimal place than this. So our slope, if you take this t with 1 degree of freedom and square it, so 73.18 squared gives us 5355.3 something. So so obviously there's some other values, decimal places that we're missing here, but they rounded it up to 5356. Okay, so this value here and this value here are basically the same, except the F statistic is the square of this T statistic. And it only works for a straight line. Once we get to multiple regression, you can't do that anymore. This value will mean something different because it will take into account all of the variables that we're using to predict. Right now, it's only taking into account age. So we can say whether or not the model is significant by looking at simply age. Okay. All right. And I have written this up the way that we should. We test the hypothesis, beta not equal to 0 versus the alternative, it's not equal to 0. At alpha equals 0.05 in the model, here's our model. The estimate for the intercept, we always give these, is here. And the test statistic is t is negative 87.78 with 9 degrees of freedom, corresponding to a p-value of 0.0001. And I don't, okay, so yeah, so that is, yeah, so it has 9 degrees of freedom, n minus 2. And then we reject H naught. There does exist sufficient evidence to support the claim that the intercept is not equal to 0 at 95 degrees confidence level using a random sample of n equals 11 observations. And then we write the same thing basically for the slope. Okay. So that's how you should write this up. The confidence intervals are given by confit, and we put the level in that we want, so we get those confidence intervals out, and they're given here. We interpret them. We are blank % confident that the interval here contains the value of the intercept in the model. We're given the model. There it is, using a random sample of n equals 11 observations. Please don't change this except to so just don't change this except the values in the model, okay? There is just no good way to change this to make it in your own words without messing up what it means. This is a very technical definition that you don't want to change. So for projects, homework, whatever, you want to leave this exactly as it is. Change the numbers here and change your model. That's it. And n. So just change the values as you need to. And then for the slope of, this should be slope of age in days. Okay, so you'll change your variable name here for the slope. You may change your model as you need to, the variables in there, and your sample size and the interval, okay, that's printed out. And I rounded this to 3 decimal places. So that's pretty standard. You could do different decimal places based on your data, but if you have a lot of precision, you may go more. If you don't have enough precision, you may go less, but that's based on the actual data that you're collecting. We had 4 decimal places in the ounces for the data, so for the weight, so we could go 4 decimal places here. I chose 3 just to keep from confusing the reader too much, okay? So there's that factor as well, but 3 or 4 would be fine as far as decimal places. Then we've got the confidence interval for the mean response at a particular value of x. So this is the confidence interval around the regression line, okay? That's what this is. But we're doing it for just one value of x. Now the computer can do it for all of the values of x very easily and create the band. I will not ask you to do that at all this way. I will simply, I think I may have code down here that does that for you, but if I ask you for a individual value, this is how you would do it. So the confidence interval about the mean value, so it's the mean value, so that's the regression line. For 7 days, that's where x is equal to 7. This gives us confidence interval 4, and that's mu of y given x naught. You could change this to log dry weight given age in days, but I wouldn't do that. This is fair enough. And it says at x0 days old. Okay, so you'd want to change this to whatever your variable is for the x. The predicted value for, and this is the log base 10 of the dry weight. That's our variable, so you'd need to change that for this. And then I have x of 0 equals 7. So if it's a different value here, you want to change that here, and then give the output. So the output is provided here. It gives us the estimate. It says fit. Here's the lower confidence band and the upper confidence band, or limit, I'm sorry, lower and upper confidence limit here and here. And so those are the values that you put into this interval. So we do this talking about the actual, what it is, and then we are 95%, so you change that based on your confidence level, confident that the interval here contains the value of the mean log of chick weight for x equals 7 days in the model here, using a random sample of n equals 11. So you modify this, tweak it as you need, but otherwise leave it alone. So instead of days, it would be whatever your x value is. Okay. Instead of log of chick weight, it'd be whatever your y value is. All right. To interpret, we need to transform these values back to ounces, back to the original weight instead of the log of the weight. So to do that, if we have the log, we need to go e to that. So we take e of this value, or I'm sorry, we take 10 raised to this because it's not log base e, it's log base 10. So we take 10 and raise it to the negative 1.318. And when we do that, we get 0.0481. How does that compare to our actual data? Well, let me come over here to Y1 and look at age 7. 0.052 is the value we get for that, and what we got was 0.0581, pretty close, but this is a little bit smaller. Okay, all right. And if you look at your regression line, you'll see that the point is a little bit below the line for this point, for the second point, okay? And now it also gives us, here's the confidence interval, and so what we've done is we've taken it and I've put it 10 raised to the power. To transform it back, you would have to modify this code if you have to transform it. I think I'll avoid giving you something where you have to transform the data, so you could just delete this portion. But this is how you do it. You do the inverse function. If we take the log, then we take the inverse of that is the exponent. If we took the sine, which I hope we'd never have to take the sine, then we take the arc sine to get back to the original units. So we're going to have to use the inverse function to transform back. That's why transformations are tedious and a little bit difficult, but they are very useful. You could not analyze this using regular regression with a curved, with straight line. We could add a square term to this to try to fit a polynomial to this, and then do multiple regression with the polynomial. That adds a level of complexity that we would hope we wouldn't have to interpret, because that makes interpretation more difficult, as we'll see. But this is probably the cleanest way to do this. Take the transformation, get the confidence interval, analyze it, but then transform it back. And so when we transform it back, we get between 0.045 and 0.052 as our 95% confidence level for 7 days. X equals 7. Okay, and we have n equals 11. So again, we analyze our confidence interval using this sentence, and then we are precisely correct. Okay. And you'll see this gives us the transformation back. But again, if you did anything besides the log base 10, you would have to modify this code. So, and I will not ask you to do that for this course. All right. Now, we want the prediction interval for a single value. So instead of being the confidence interval about the regression line, we want the confidence interval about a single point, okay, a single value. And so a new value for log y at x0 equals 7. So we have this code here that we use. And so this is automatic. You'll notice that it gives you the same estimated value here. And that's as it should be. The estimate of the point should be the mean, right? But now the confidence interval for the individual point is going to be bigger. 1.389, 1.247, and these are both negative. So here's the interval here, 1.389, 247. You'll see these numbers are closer to each other, 1.349. This is 1.389, so further away from 0, 1.247, and 1.287. So this interval here is smaller than the interval. This interval is bigger. And that's what we expect for an individual point instead of the mean, okay? So we give the predicted value here, and then we give the confidence interval here. So again, you're going to have to modify your model. Log of chick weight, you're going to have to modify that variable for y, or for x, I'm sorry. No, that's y, yes. And x is days, or age, age in days. So you're going to have to modify that, and your sample size, and your model, but it's still just tweaking compared to writing it from scratch, okay? To interpret again, we need to transform back to ounces, not log of ounces. So again, I've given you the code here to do so. Again, I will not ask you to do this on homework where you do a transformation, so you'll be able to just delete this chunk of code and not worry about it. You'll get the actual data here, because we won't use a log or other transformation. But I wanted to show you how to do that so that you have this in case you need it in real life, okay? So we transferred back. Here's the value, 0.0481. And again, looking for 7 days, this is 0.052 versus 0.0481. And then we get 0.041 to 0.0576. So this should be 0.058 if I want to go to 3 decimal places. My cat Pippi says hi. She is wanting me to spend time with her. So if you hear her in the video, that's her saying hi and telling me to go faster so that you can relax more. All right, sooner. Now, here's the confidence bands about the regression line. So this is for the means. So I've given you the data here, or the code here, so you'll have to change this, of course, variables and stuff, but it's all tweaking. All right, and then change what the graph says. So here's age and days for X, log base 10 of dry weight, etc. Okay, so you can change that, and when we run this, well, need to run this. There we go. So here's what I was talking about earlier. We have a problem. Some of the points are a little bit out, but look how close those lines are to each other. Okay? And also notice that I'm going from -2 to positive 0.5. So I should make this symmetric about 0. So let's make this 2 to 2 for the y. And in this case, I can control both. Okay? Because I'm using a plot, I can control both the limits. And so you'll need to plot it and keep on going until you've got all the points included, both x and y. Okay? So this, using the symmetric graph here is always nice, about 0, when we're talking about something that goes below 0 and that's both negative and positive. So the log does that. For others, we would just worry about getting the limit on there. In fact, either one's okay in this case because it's not residuals. If it was residuals, I'd certainly encourage you to make these symmetric about 0, but these are not residuals, these are just log. So this gives you all the points, and you can see that they're very close to the line, but so are the confidence bands. So, so I've written up what we see here. The log transform data is very small and provides a good linear fit. So this is supposed to be a test of whether the regression line is a good fit. But the limits are so small that it's not practical to say, hey, they've got to be inside these limits. Now we're going to look at the prediction bands. So we call these confidence bands because they're for the regression line. And then we call them prediction bands for the values. Okay, so these are going to be the bigger confidence intervals. And so we can see that all the points are within these individual bands, and we always expect that. We also usually expect that they're in the confidence limits for the regression line, but in this case we did transformation and it's so close to 1 that there's just not a lot of variation to create a confidence interval for it. Okay, so from a practical standpoint, you might theoretically say that you reject the linearity of this, but if you look at this, do you reject the linearity of it? Because I do not. Okay, so practically speaking, this is a great model. All right, I'd love to use it for prediction. I'd love to get a model as good as this in real life. Okay. So not that this is not real data, it is, but it's a very small sample size. Okay, so here are both of those. Again, you can tweak these to make them correct, but I do say that all the points are within the bands, and the 6 point is just inside, but this is a good fit. And we're going to just do some basic verifications of assumptions. There are a lot for regression, and I encourage you to take Stat 325 at University of Lynchburg because it's a great applied regression course, and we talk about all of these ways to do the analysis and make sure that we're in good shape and that we have a great model and that we can use it for prediction. We're just going to do the basics, just as we did for ANOVA, the same 4 graphs. So we're going to do a plot of LM2, and then we're going to analyze all 4 charts. So you can see this wiggly line looks horrible, but I cannot change or control the limits. Look how small the limits are. They're only from -0.04 to positive 0.04. And so when you look at this, if you were to zoom out to say -2 to +2 for these limits, which is a the normal or the practical thing, you expect most points to be within +2 and -2. You'd see how flat this line is. It's a very flat line when you change the scale to bigger, which is what we need to look at. Okay, but unfortunately the software doesn't allow to do this. We would have to graph it manually, and I'm not going to make you do that. So we just need to be smart enough to look at this and say, you know, that's really tiny. And if we zoom out from -2 to +2, this is going to be a flat line, and we're just not going to see much variation across this because all these points are from -0.0 maybe 5 up to 0.03. That's all the variation we have. Now, each point has a different fitted value because this is a continuous random variable, not a factor like we did in ANOVA. So that's one of the major differences here, is that we're using regression when we have a continuous variable for x, which is age, okay, not a factor. And so, by the way, regression and ANOVA are identical. They're just different forms of the same thing. We use ANOVA when we have factor levels. We use regression when our x variable is continuous. So instead of categorical or ordinal, we use ordinal or categorical, finite, ordinal, or chosen values where we don't consider anything in between. So we make it factor levels. We do ANOVA. When we want a continuous variable so that we can predict at any value or range, then we use regression. Okay, so we're looking for the amount of variation here versus, you know, in the middle, say, and over here. We're wanting to look at that. So we have a point down here, a point up here. It's a little big, but then we don't have enough points to really say anything. We don't have any repeats, so it's hard to say what the variation at this fitted value is, or this one, or this one, or this one. So we really just don't have enough points to make that. So we kind of have to group points together. So this one I'm going to say is by itself, and then I'm looking at these three, and there's not much variation. I look at these three, it's a little bit bigger, but remember our scale is tiny. And then I can group these four together, and it's about the same. So this is a little bit bigger than this. This is a little bit smaller than both this and this, but this and this are very close to each other. So I really don't see much of a change in variation across the fitted values. It's better to have more points, but when you have few points, don't overanalyze it too much. I've read an analysis of this where somebody says in the middle here, the points are lower. You have negative residuals for middle values, middle fitted values. Okay, but look how close they are to 0. So they're really, I mean, if these were down at, if this scale was from -2 to +2 here, then I would certainly agree. But this scale is from 0.04 to +0.04, negative to positive. So it's tiny. So I don't see any violations here. We don't see a funneling shape. We don't see, we see a pattern here where it dips in the middle and goes negative, but it's very, very small. Okay, we look at the QQ line for normality. This point seems to be the furthest away, but it's in the tail. All the other points are nice and close to the line, so there's no issue with normality. This has a bigger scale here. This gives me more of a concern than anything, and we see a decreasing. The problem is we've taken the square root of very small numbers, and so we've inflated them. Most of the time, this scale, this is a reduced scale. But for the log, when we take the square root and then we have a small variation or standard deviation or standard error that's below 1, we're inflating things. So we're blowing this up. We're exaggerating this. And we do see a trend. So this is the most concerning graph on here to me. All right. But I have to remember that I'm using the log, and so with the log I expect to see a trend in one direction or the other. Okay, that's the way the log works. And so then I do see a funneling effect here. I see small variation here, I see larger variation here. And so this chart concerns me. Okay, Unfortunately, there's not a good way to test this because we don't have factors here to test the variance across here. So all we really have are these graphs. So we have to make a determination. Are we concerned? Are we really concerned that the variance is different for across the fitted values? So for the log, when I look again at how well this fits the line, I'm not that concerned. But we see that because the limits are so small, it looks like the variation is really big. We see these points from here to here in the center, they're below the center line. And then these points are above, these points are above. So when you look at the relativeness to the line, all the points seem to hug uh, the confidence bands, okay? And that's what we're seeing in this plot, that these points are away from the confidence band. But we have such a small amount of variation that I would say that this is not going to significantly impact our effects. But I would not expect you to be able to interpret this way. I would expect you to just simply look at this, say, I see a funneling pattern and a downward trend, a consistent downward trend. The scale is not tiny, so this is a concern. That's how I would write it up if I were you. And because again, this takes a lot of experience to be able to say, this is not this is really based on everything else. I'm not very concerned about this, but formally speaking, I would be concerned about it. Okay, so I hope that helps a little bit. I know it's a confusing thing to have something where you have an exception, and unfortunately, this example is an extreme exception in that way. Now, the last chart, all we're looking for here are these limits violated? And we don't care about the 0.5, we care about the 1. That is the standard for the industry for interpretation. We don't want points beyond the Cook's distance of 1. Okay? There's other ways to get the actual Cook's distance for the points, but we see that all of them are even within the 0.5, so there are no leverage points or influential points or outliers according to this. We are concerned if a point is outside of 1, on either side of this. Why? Because that makes that point really important. It by itself will shift the regression line significantly, and we don't like points that do that. Luckily, this model doesn't have any. So I've written up the analysis here, so please take a look at it and read through it so that you understand what's happening. I've not put a summary here, but I did put a summary. We do not have strong evidence that the assumptions were violated. I say, note, there are many additional checks for regression that are not included in this course. You would want to take Stat 325 Applied Regression to get those. That's it for this video. If you have questions, come to office hours. I will be happy to help you. If you need help before then, email me, but make sure you email me a picture of the picture of the problem and your solution so far. If it's code, email me your code so far and ask your question in the email. Let me know, and I will get back to you as soon as I can. So please take care of yourself and stay safe, because we hope to see you next time.